And so one concept that I want to try to think about is the idea of chargeable bodies. So rather than talking about individual particles of protons and electrons, well, what we know is that we can actually populate an object with charged particles or evacuate charged particles from an object. And different objects allow one to move charges around in a different way. And so we're going to introduce two types of chargeable bodies. All right, and so the two types of chargeable bodies have very, very different characteristics when they're charged. The two types are going to be a conductor and an insulator. The first one, the conductor, is the one we use very commonly when we're doing something like building a circuit, wiring, that sort of thing, because this type of material allows charges to move freely. So this is material which allows charge to move freely. And I mentioned that that's the kind of thing we'd like to do in wires, and you and I both know that wires are made out of metal. And so it turns out that metals are quite good at conducting charged particles. Now, it's a specific type of charged particle that gets conducted, that moves around freely. And specifically what I'm talking about here is, of course, the negative charges, right? The electrons. That is what freely moves around in a conductor. And so metal that we can use, all kinds of metals are really good conductors, but let's use copper, because copper is a common material used in wiring. The opposite of a conductor is an insulator. And so in an insulator, this is a material where electric charges are not able to move. And so it really is quite the opposite of a conductor. While a conductor allows charges to move around freely, the insulator doesn't allow them to move around at all. And what I'm basically describing here is a perfect insulator and a perfect conductor. But most materials are not any of those things. Usually what we have is that a material is a good conductor and a poor insulator, or a good insulator and a poor conductor, as opposed to being perfect at its job. And so these are idealized sort of definitions, but we can make use of them for our purposes. But just keep in mind that, copper is not a perfect conductor. And so an insulator can, we think of an example of a good insulator, something that won't allow electricity to flow along it very well or charges to move at all. I think I can guess a few suggestions. All right, so now what we want to do is try to understand Coulomb's law a little bit better. And the way we're going to do that is to actually compare it to something that we know, I would say, much better and certainly more instinctively, and that is gravity. And we're not going to talk about the simplification of the force of gravity on Earth, F equals mg. Instead, we're going to talk about the universal gravitational equation that we got from Newton, and most people will have done this in a previous physics course, but if not, it's pretty easy to understand, and our kind of instinctive knowledge of gravity will be very interesting to compare. So let's see what we can learn about Coulomb's law by comparing it to Newton's universal gravitation law. And so we'll start by writing the equations down. Our old force equation for Coulomb's law right now, we'll call it Fe for the electric force, is given by K, Q1, Q2 over R squared. And we'll write it in the vector form like so. Now if we compare that to Newton's law, we have Fg, but again not equal to mass times gravity, but our universal equation, which is big G times m1 times m2, all divided by r squared, r hat. And when you look at these two equations, Coulomb's law and our gravitation equation, there is much similarity that we see between the two of them. Clearly we see a constant for both of them. We see the dividing by the distance between our objects squared. And so while the right-hand side is going to give us the force of gravity due to one mass onto another mass separated by a distance r, the Coulomb's law is giving us the force of one charge on another charge divided by a distance r. K and G are obviously very different from each other, as we'll see. But rather than dwell on the similarities between them, because I think they're quite obvious, let's look instead at the big differences between them and see what that can tell us about our Coulomb's law. And so at this point, you may want to pause this video and see if you can make a list of differences between both the force of gravity and the force of the electric force. And so the first one that really jumps out, I've kind of already said, has to do with the big difference between our constants, K and G. Well, K, the Coulomb's constant, is very, very large. Our big G, that is Newton's constant, is very, very small. And in comparison to one another, K is much, much bigger than G. And what that implies is that the force, the electric force, is stronger than the gravitational force. If the other quantities are going to be approximately equal to each other, then K, being much larger than G, is going to make it a stronger force. But you and I know that that is not the case when we get to the largest scales. When we get to very, very large scales, clearly our dominant force is gravity over the electric force. Can we think of another big difference between what we learned about gravity and what we learned about the electric force? Hopefully some of you said that another big difference has to do with the fact that the electric force can be attractive and repulsive. While what we've learned about gravity is gravity only attracts. So that seems to be a significant difference between the two. Gravity is only attractive. All right, and so the last one that we're going to think about does explain away the fact that the gravitational force, despite having a much smaller constant, is actually a much stronger force on the largest scales. Once you start getting to the sizes of asteroids and planets and galaxies and large chunks of the universe, the gravitational force is the dominant force in determining what happens in the universe. It plays a much larger role than our electric force. And the reason has to do with the fact that all objects have a mass. All objects have some mass, and the more mass you get together, the larger the mass is and the larger the gravitational force is. But when it comes to electric charges, there are plenty of objects in the universe that have a neutral charge. And even if we had a whole bunch of negative charges, we probably also have a whole bunch of positive charges, and adding them together gives us probably a very small q. And so while m can get larger and larger and larger and larger, from atoms to rocks to asteroids to planets and stars and galaxies and whatever, our charges don't necessarily accumulate into larger and larger charges because of the positive and the negative and the neutral. They tend to stay much, much smaller. And so let's write it this way. An object can have no net charge. No net charge. And therefore, no electric force. As we know, there's no electric force associated with the neutral charge. And on the other hand, all objects have a mass and therefore a gravitational force. So not all objects have a charge, but all objects have a mass. And therefore a gravitational force. And what all of this is implying to me is that the electric force should be more significant on a smaller scale than the gravitational force. And then as objects accumulate mass, the gravitational force eventually takes over as a more important force. And so let's write this. On large scales, gravity is more important. Because mass is additive. It can only go in one way. It can only get larger and larger and larger. But with charges, we know it can go both ways. You get a plus and a minus and a plus and a minus and a plus and a minus. And you add them all up and you get something very, very close to 0. And so even though our constant, little k, is a large number and big G is not, gravity will dominate on large scales. And you and I know that from our everyday experience because we are pretty large scale. We can experience the universe on a large scale. We're stuck here on the planet Earth because of the huge gravitational force between us and the Earth. But if we go to a much smaller scale with a small mass, we'll quickly see how important the electric force is in comparison. And so why don't we do that? Why don't we calculate both the electric force and the gravitational force for something very small, like a hydrogen atom. And so this is just a fun little example for us to compare the electric force and the gravitational force. So let's give this a try. What is the electric and gravitational force in a hydrogen atom? And when we think about hydrogen atoms, what we're going to be doing is measuring the electric and gravitational force and a hydrogen atom between the parts of the atom. And so specifically, a hydrogen atom is essentially made of an electron and a proton. And we want to measure the gravitational force between that electron and proton, as well as the electric force. And so giving you a picture of what we're talking about, and this is really an incorrect picture as we know. Let's put our large proton there, Q1, right in the center, and then beside it, in an orbit, is our electron. And this is a improper simplification, but we'll just imagine that it's going around the charge like that, and we'll say that it remains a distance r away, and we'll give that value as well. So we've got an electron, we've got our proton. We're going to need the masses and the charges of each, so I'll go ahead and I'll write those down, but I expect that you will do this calculation. We've got the mass of the electron is 9.11 times 10 to the negative 31 kilograms. Very tiny. The mass of the proton, much larger, but still small, 1.67 times 10 to the negative 27 kilograms. The radius, that is the distance between, or average distance between our electron and proton, is small, 5.3 times 10 to the negative 11 meters. And we've also got our charges. They have the same magnitude of charge, and we're only worried about magnitudes, so we'll give them together. It's one elementary charge. Let's use 1.60 times 10 to the negative 19 coulombs. And that's all we need other than our constants. And so we've mentioned the constants a few times. Just to remind yourself, big G is 6.67 times 10 to the negative 11, while our little k is, we'll use 9.0 times 10 to the 9. You can use 8.99 if you want. And what I'd like you to do is to take those values and plug them into our very popular equations here. That is into our electric force and our gravitational force equation. So do that now, and let's see what we get. So I'll expect that you have paused the video, that you've taken your calculator, and you've got your two forces. These are the values that I got for these forces. Please compare. I have the electric force being 8.2, just to 2 sig figs, times 10 to the negative 8 newtons. Wow, that's the smallest force I think I've ever dealt with in first year physics, while the gravitational force is smaller still. Much, much smaller, in fact. 3.6 times 10 to the negative 47 newtons. So insignificant. It is very close to nothing, and clearly is much, much smaller than the electric force between a proton and an electron. And so this, in combination with the other two fundamental forces of nature, kind of creates a scale to where the different forces are the most important. And when you're on small scales, all we've found out is that the gravitational force is very, very tiny and much, much smaller than our electric force.